All right, so these are the use cases that we plan to cover today. I will be covering, along with Elsa, the content delivery networks, and then it'll be followed by the Lightbits Labs discussion, as well as DAOS and some VMware. So content delivery networks that I'll be referring to over and over again as CDNs for the sake of saving some words. So if you're not familiar, content delivery networks are a type of networking appliance and networking workload that have grown out of the expansion of the internet over the preceding decades. So in today's world, most of the web activity that you do, or as the average person, involves a CDN in some way or another. A CDN may be used to serve images when you are shopping online, or it may be used to serve video, whether that is live video like we are currently using today, or it is pre-recorded video. And so in 2020, for instance, with the pandemic, the amount of consumption of on-demand video and live video skyrocketed. So as you can see here on the slide, we have 4 billion hours of viewing in 2020, which is causing a serious need to expand the performance capability and capacity capabilities of CDNs. Additionally, the resolutions that people are viewing at are expanding. 4K video is becoming more and more common, and the networking technologies have evolved to make that more possible. The displays have been able to display 4K for quite some time, but actually getting that 4K content to the end user has been quite challenging. One of the things that contributes to that is 5G networking for mobile devices. Additionally, the library sizes have been growing as well. This is partly due to the fact that many of these content providers and CDN providers have been around for quite some time now, and over time their libraries have grown, but also they're trying to serve more and more customers with more and more varying interests, and as a result that also causes the libraries to grow, along with an increase in size due to the many resolutions that they have. And 4K in particular results in a very large compressed video file relative to other resolutions like 1080p or 720p. Additionally, the number of subscribers is growing. Most of these CDN service providers report every quarter to their shareholders that they have more and more customers. And so to solve some of these problems, CDNs are tiered, as you can see here on the right-hand side of this slide. So a typical CDN will have an origin, which is the authoritative repository of the content. And there may be more than one origin for failover or to handle the capacity or the number of customers. And then you'll have some middle tiers of caching. And you may have, let's say you operate a very large CDN. You may have one of these per country or one of these per continent, or if it's a very large customer base, you may have more of them as well. And then you will have a last line of caching that is we're going to refer to as the edge tier. And the edge tier you typically have the most of. These are very, very distributed. And so you may have several of these per large city to handle the workload from your subscribers or end customers. And so as you go through these multiple layers of caching, the performance and capacity requirements change. At the mid tiers, the performance requirement is generally reduced relative to the edge, but the capacity requirement is increased. The goal of any of these CDNs is to cache as much as possible to save on traffic to the next tier up. And so at the edge, you cache at the edge to avoid traffic to the mid tier. At the mid tier, you cache to avoid traffic to the origin. The edge tier, as opposed to the middle tier, is much, much more focused on performance. And as a result of this, the cost is typically increased relative to the mid tier, and the capacity is typically decreased relative to the mid tier. So today we're going to focus on two main content delivery network workloads, both of which are video, but they're two different types of video. The first that we're going to talk about is live linear video. Live linear CDNs typically use memory for endurance and performance reasons to cache video content for a relatively short period of time prior to delivering it to the end customer. And so today we're going to talk about using Optane persistent memory to increase memory capacity at a lower cost than DRAM while still achieving an approximately 200 gigabit per second performance level. The other workload we're going to discuss is video on demand. This is probably the one that most of us are more familiar with. This type of workload has been around a little bit longer. And so a video on demand CDN will typically use flash devices as well as some memory at the edge, where the bulk of the content that's cached is stored on the SSDs. And the hottest content, the most accessed content on that edge node will be stored in DRAM. So if we talk about live linear specifically, live linear video streaming is most similar to the traditional television model. The content is not necessarily determined at will by the viewer, but is instead broadcast out over internet protocol to the end users. So some examples of this type of use case would be Sling TV or AT&T's Uverse. Live linear providers typically cache a few minutes of content for every channel and resolution to allow for users to be slightly out of sync with one another and to enable pause or rewind features. And so with this workload, there's a need for increased memory capacity, and that can be solved in one of two ways. You can spend more money for DRAM, or you can spend less money for a similar capacity and use some DRAM and some Optane persistent memory.
So Nash, this is Ray Lucchese. Is it the reason you couldn't put this like on NVMe SSDs or Optane SSDs is because the response time required is so hot, or it's the throughput issue, or what?
It is, to some extent, it is both of those. So for live linear, the latency is a concern, although I would say more the consistency of that latency and how predictable it is than the absolute latency. For instance, in a video or a live linear setting where this is going to traverse the public internet to the end user, a few nanoseconds wouldn't make much of a difference. But a sudden spike of, say, 5 or 10 milliseconds would make a difference.
Yeah.
The other main concern here for why you would use memory or Optane persistent memory in particular instead of NVMEs is endurance. So typically you maintain a buffer that is a couple of minutes, and that is going to be constantly overwritten. And so if you're constantly overwriting that, you can very quickly wear out a flash device.
I gotcha. All right, thanks.
And so actually on that topic, the live linear use case will consume a lot of memory capacity as well as a lot of memory bandwidth to maintain this relatively short video buffer. That video buffer will vary depending upon the operator. Sometimes it's 1 minute, sometimes it may be several minutes. And Optane is particularly suited to this because it offers additional capacity over DRAM at lower cost. So the configuration that I'm going to talk to you today about is an Optane persistent memory configuration where we have 2 terabytes of total memory capacity. And since we're using the Optane persistent memory in memory mode, what that means is that we have 2 terabytes of Optane persistent memory, and then we have a small amount of DRAM that the memory controllers will use as a cache transparently to the user with the Optane persistent memory. So Optane has very high endurance, which is critical to handling the constant overwrites that this workload is going to do. And so for this testing in particular, we're using a piece of software called Varnish, specifically the enterprise version of Varnish. And so the way that Varnish caches content is somewhat unique. Varnish manages its own memory rather than relying on the Linux operating system to manage it for it. And so in Varnish, now I'm showing all the layers here, not necessarily all of these are in use in this particular case. So the Varnish web server will run, and we'll use something called MSE, Massive Storage Engine, which will, if it is instructed and configured to address disks, will configure a flat cache file on those disks that will, run on top of the file system, ext4, XFS, which will run on top of the Linux block layer, which runs on top of the Linux kernel. MSC also has a feature, though, where we can specify an amount of memory to use. And so in this case, we've told MSC to use 80% of the total memory in the machine, which is about 1,800 gigabytes, for caching. And so when the clients access the content, that content will be cached on this node, and we will avoid traversing all the way back to the origin that is typically much slower and much further away. And so in this case...
So Nash,
go ahead.
Are you saying there's no DRAM other than the sort of the cache in front of the PMEM in these sorts of systems? I mean, what about the instruction cache and that sort of instruction memory? Is that coming out of PMEM as well?
So the caches on the processor are unchanged.
I got that.
In terms of the memory itself, the way that the memory controller manages it is that it displays to the operating system the 2 terabytes of total capacity. And it is not shown to the operating system or the end user whether a particular piece of data is on DRAM or is on Optane.
So it's effectively the whole instruction memory is also sitting on this Optane DMEM.
It is possible, but relatively unlikely. The memory controller will do caching of its own.
I see. So it'll cache instructions in DRAM that it requires.
Yes. So the most accessed information, whether it is a piece of data or code that's about to execute, is very, very likely to be in DRAM.
But effectively, this whole system is really running out of this Optane DRAM configuration completely.
Yes. Yeah. From the operating system's point of view, it just knows that it has 2 terabytes of memory.
Yeah.
Which makes it really easy for an application to use. If your application can access memory through the Linux operating system, it can access Octane.
Yeah, I got it. Thanks.
And so in this configuration, with the testing that we did, we took some feedback from customers. And with that feedback, we identified 200 gigabits per second per edge cache node as a interesting performance and cost crossover point. And so that's what we architected this system to do. This system is able to achieve nearly 200 gigabits per second at better cost than a DRAM equipped system. And this allows you to have extremely high cache rates and a very large number of channels where, if you think about this in terms of television, although this is not the same thing as television, your cable subscription may include 1,000 channels of possible things that you could watch. So in this case, we have 760 channels where each channel has multiple video resolutions to handle multiple clients. And we are caching 93.3% of requests. And so only 6.7% of accesses will ever touch the origin. In this workload, it's very difficult to hit 100% cache hit rate because of the size of the buffer and the fact that the buffer always changes. And so if this is live video, we're constantly going to be adding new live content as some segments of video fall out of the cache. So are there any other questions on live before we move on?
Just to be clear, there's no disk storage or other SSD storage sitting behind the system other than perhaps a boot disk or something of that nature. And if there is a cache miss in the server, it goes back up to the mid-tier to go retrieve that segment.
Yes. If you wanted to, so there's nothing preventing you from installing disks in this machine. However, if you did, you would want to, most of the time at least, you would want to isolate them from this particular request path, because you would end up resulting in a lot of extra wear on those SSDs without a whole lot of benefit.
I got you. All right, thanks.
But you could dual purpose this machine and have it handle this workload as well as some other workload if you wanted to. Now, there would be some cost and performance trade-offs involved in that, but the technology allows for it.
All right.
So you just said that you can have live video with additional workloads, meaning live video and video on demand on the same machine is something possible. Does it make sense to reduce the cost, or you have two different infrastructures?
The primary use case that I see for that dual purpose machine is one that is handling both workloads, but not necessarily at the same point in time. And so if this was say a virtualized environment, rather than this bare metal environment, in a virtualized environment, you could configure two virtual machines and spin up one or the other depending upon the workload that you're trying to address. And so you could have a virtual machine that is pre-configured to handle video on demand and access, say, a small amount of memory and the full fan out of NVMEs installed in the machine. And then you could also have a VM configured to access none of those NVMEs, but access a very large amount of memory to handle that live linear workload. And so one thing that some customers have expressed interest in, particularly the ones that do run virtualized environments, is having machines that primarily handle video on demand, but during periods of peak load will transition to handling some or all of the live linear workload. So if we look at video on demand, this is similar in terms of the intent. We want to cache at the edge so that we avoid hits at the mid-tier or at the origin. The software is similar. This is the same Varnish Enterprise. The difference here is that we're using the layers of Varnish Enterprise that we were previously bypassing. And so now we have MSE configured to use memory, in this case, a small amount of DRAM, as well as the flat files that it would lay out on the file systems that reside on the NVMEs, and then go through the Linux block layer and so on and so forth. And so for video on demand, the performance targets are a little bit different because the workload is a little bit more manageable. Higher cache hit rates with video on demand are much more feasible because you can, say, preload content onto the cache during periods of very low utilization. So you could say at 2 o'clock in the morning when most people aren't watching things, they're sleeping, you could preload content that you expect to be popular in the next day or the next week or the next month. And so that changes the performance targets a little bit. And so some examples of video on demand providers that you're likely to be familiar with would be Netflix or Disney Plus. So the video on demand workload is a little bit different from the live linear workload, not just in its performance characteristics, but also in its capacity requirements. Instead of caching only a few minutes of content, we're going to be caching, for instance, entire television episodes or entire movies and many of those. So we may have hundreds, if not thousands, of hours of content on this machine. It's a read-intensive workload because with it being on-demand viewing and we preload content, we'll have very few, comparatively speaking, writes and a overwhelming majority of reads. And given that this is video at relatively high resolutions, these are typically large reads. And so in the configurations that I've tested for this, we ran two different types of edge cache system. We ran one that was a single socket configuration, where we achieved 191 gigabits per second on a combined 200 gigabit per second line rate. And then for customers that want to scale up to higher performance to handle more users or higher resolutions or both, we also did a dual socket configuration that got very good scaling, linear scaling, up to 383 gigabits per second on a 400 gigabit per second combined line rate. And so this is possible in part due to the storage media, but also due to the software. So the software in this case is taking advantage of the fact that this is a NUMA balanced system and is saving extra memory copies as well as additional latency of traversing UPI unnecessarily. And so that helps to improve the efficiency of the machine, improve the latency, and improve the throughput.
Yeah, wait. So the solution, in this case, video on demand, doesn't have PMEM? Is that how I read this?
In this particular configuration, it does not.
But it could potentially be using Optane SSDs or your QLC SSDs, depending on performance requirements and that sort of thing.
Yes. So this configuration that I tested was using TLC, Intel 3D NAND, NVMEs, so P5510 in particular. You could use Optane SSDs if you wanted to. I suspect that in most environments, the size and cost of those devices would be an important factor relative to the TLC or QLC devices.
I got you. And what's a typical cache hit rate for a video on demand edge solution? You mentioned, I think, 97 or 93% for the live linear.
Yes. So for linear, we did 93%. For this testing, we did 100%, which is pretty close to what some of the more sophisticated video on demand operators are able to achieve. A lot of the video on demand operators have a pretty intense knowledge of what their users want to watch at any given moment in time.
Yeah,
and can preload stuff. Can preload the content in off-peak hours, and then so in peak hours you have almost 100% hits.
I got you.
So cache hit ratios above 95%, or in some cases 98%, are not uncommon.